we have seen that one can get a lot of information about the system vibrations, stability, rates of transitions by studying the potential energy surface, U. However, calculating it quantum mechanically is a rather complicated and expensive job. Um, so in many cases, for example, biological molecules, when you have a large number of atoms, this calculation is so expensive that cannot be actually performed, or can be performed only in simplest cases. So from the early era of molecular modeling, people have been trying to devise a simpler means of studying reactions in condensed matter systems, vibrations, studying stability. And this has been done using so-called classical force fields. So classical force fields is basically a simple idea when this potential energy surface is represented approximately by a set of analytical functions, which are easy to calculate, um, do not require any self-consistent solution of, say, DFT or Hartree-Fock equations, and therefore, if chosen appropriately, may serve as a very good tool in studying condensed matter systems. So, classical force fields. The simplest classical force field is based on pairwise approximation, when you have atoms in the system and the total energy of the system is built as a sum of all pairwise interactions between any pairs of atoms. And the simple form of this pairwise interaction is based on the so-called Lennard-Jones potential, which is written here. And this Lennard-Jones potential has this quite characteristic form with some minimum at some position around sigma. Sigma is a parameter, and another parameter is epsilon. And at that position, sigma, no, actually it's sigma times this prefactor, 2 to the power of 1/6. The energy is minus epsilon. So this is kind of a characteristic interaction between two atoms, neutral atoms, and the total energy is built as a pairwise sum over all pairwise interactions in the given system. The important feature of this interaction is that it depends only on the distances between atoms. And that approximation therefore works only in the case where we do not have directed interaction between atoms. For example, it could approximately work for inert gas, solids, or in metals. But it's not a very good approximation for covalent systems or H-bonding systems. The first term in this Lennard-Jones potential is responsible for the repulsion between atoms at short distances. It has the power 12. And the second term with the minus sign, attraction, and the sixth power is related to van der Waals attraction between atoms. In crystals, interaction between nearest neighbors and next nearest neighbors is the most important one. And because close packing is dominated, the number of nearest neighbors must be optimized. In biological molecules, many interactions are directed. Either you have a covalent bonding or you have hydrogen bonding, and therefore the analytical expressions which are chosen to represent the total energy of the system as a function of atomic positions would contain various terms which reflect the bonding in this particular system. So you can distinguish a few types of interaction. First of all, you have a two-body interactions, this pairwise interaction, which depends only on the distance between two atoms. You may have three-body interaction, which depends not only on the distance between atoms, but also on the angle between them, or could be the third distance. As an example, you have a water molecule, for instance, in which total energy expression, you may have interactions between hydrogens and their oxygen, and between two hydrogens, or three body interaction, hydrogen, oxygen, hydrogen, which depends also on the angle between these hydrogens. Also, the more complex types of terms exist. And of course, if the system is charged, there are charged atoms, there are also Coulomb interactions which need to be added.